If you've ever been victimized by Regina George, raise your hand. Now, I decide to rank my friends, but I want to make it objective, so I decide to do it based on how often I have to leave them to go find more food. I make a ratio of me leaving my friends versus me with my friends, where the more often I leave my friends to find food, the worse of a friend they are, or the more often hydrogen leaves the acid, the stronger the acid is. In chemistry in general, whenever you have a fraction of the products over the reactants, it's called an equilibrium constant. And in this case, it's the equilibrium constant for an acid, so it's the Ka. Analyzing the fraction itself, if you see that the numerator or the top number gets bigger, or there are more acids being made, or you see the denominator, the bottom number, getting smaller, that means overall the fraction itself is going to get bigger, or the Ka is going to get larger. The same is true of the reverse. If you have fewer acids being made, or a smaller number in the numerator, or a larger number in the denominator, or more hydrogen still bound to the acid, you're going to have a smaller Ka. After counting for a while, it was clear some of my friends gave exponentially more than others. So I had to make a new kind of graph where each exponent just raised it by 1. In math, this is called a logarithmic scale. Now, I also wanted to make it so that worse friends had lower numbers on my ranking system. And the way a logarithm scale is set up, in order to do that, I would have to flip the fraction or make it the negative logarithm. So it would either be the positive logarithm of HA over A, or the negative logarithm of A over HA. Whenever you put something into a logarithmic scale in science, it's always called a P. So because this is the P of a Ka, we call this the pKa. The more often I have to move to go get food, the less happy I'm going to be. You can think of my percent happiness as a relationship of how often I'm having to move. The pH, my percent happiness, is the negative log of the hydrogen concentration, or how often I'm moving to go get more food. Now let's say I'm trying to choose between two friend groups. I know how often one friend shares food with me, but I'm not really sure how often the other friends are going to share their food. So to figure out where I'm supposed to go, if I know my friend barely shares their food with me, so their pKa is pretty low, and I know the other group that I'm thinking about joining, those people look a lot happier than my friend is, I'm going to choose to move to where the people are who are happier. When other people share food, it doesn't necessarily make them happier. There are going to be less people that are happy. If 5 people are having to share food for every one person that's getting food, there's going to be fewer happy people. So the pH, or the people who are happy, is both a measurement of the negative log of the hydrogen concentration, or a measurement of the pKa plus how much more hydrogen is moving within the system. If you know the pKa of one of the molecules and you know the pH of the solution, you can figure out if the pH of the solution is going to change when you add the new molecules, how much it's going to change, and if it's going to go up or down based on a relationship between the pH and the pKa. If the pKa is higher, then you can anticipate that the hydrogen is going to want to leave those molecules and go into the regular solution. And when there's more hydrogen in the solution, it lowers the pH. So if the pKa is greater than the pH, it lowers the pH of the solution. In contrast, if the pKa is greater than the pH of the solution, then some of the hydrogen from the solution is going to bind to the new molecules that are being added to the solution. And because there's less hydrogen freely floating around, that's going to increase the pH of the solution. When the pH is equal to the pKa of the system is said to be in equilibrium, where no hydrogen is moving and the pH won't change.